Hi, I'm Professor Goings. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in pretty much any college mathematics course, please consider subscribing to our channel, watching our videos, liking, sharing, commenting. All those things are greatly appreciated and help our channel to grow. Let's go ahead and get into the current video. We're going to take a look at what it means to have a continuous function between topological spaces. If you haven't watched the previous video on what is a topological space, go ahead and watch that, because I'm going to assume you know what a topology is and what a topological space is throughout the discussion here. Now, in your calculus course, we have the concept of continuity, where we informally you can draw the graph without ever lifting your pencil, or more formally we've got the epsilon delta definition, and then in a more generic sense or a more general sense we've got in a metric space, similar to an inequality, but we might have a different metric. What I want to do is I want to talk about continuous functions in a much more abstract sense, being a topological space. On a topological space, I only have two things. I've got sets that are open, which is your topology, and then you've got the set itself, meaning I've got points. Well, if I have a function between two topological spaces, my definition of continuity is going to have to have only two things. So there's definition of continuity. So the definition of continuity between topological spaces has to have a couple requirements. One, use the topologies. So in other words, my definition is going to have to use the topology of the domain space and the target space. Two, use the function in question. So I'm going to have to somehow relate the function itself to these open sets or to these topologies. And three, I want it to reduce to the epsilon delta case. That means if my topological space happens to be, say, the real line with the usual topology, then I want this abstract definition to reduce down to that. So in other words, this is just generalizing the epsilon delta situation. Now let's take a look at a continuous function, again in sort of a pre-calculus calc sense. If I give you the function f of x is equal to x squared, okay, so my graph looks like this right here. Again, we know that that's continuous because I can draw the graph without lifting my pencil, or it's got the epsilon delta definition with x squared. But I want to consider something that is fairly abstract, and you're probably going to be like, well, where in the world does that come from? I want to take a look at an open set. In other words, more specifically, an open interval in the range. So I'm going to call this set I. So I is going to be that open interval in the range of the function. Now let's look at all the elements of the domain that map to those y values. In other words, let me see if I can try. I think this pink works a little bit better. Okay. Everything within those two intervals down here on the x-axis, everything inside those two intervals map to this in the y values in the interval I. And so the idea is that for that open interval I, the pre-image of I, pre-image of I is, well, let's just say this is the interval j, and then this is the interval k. So it's j union K. Now J and K are both open intervals. The union is of course open. And the idea is I could take any open interval in the range and its pre-image is also going to be open. So for this function to be continuous, pre-images of open sets are open. Okay? This definition right here, or this concept right here, uses the topologies of the domain and the range space. In other words, open interval in the range, open intervals in the domain. I use the function, I used f, and it does reduce down to the epsilon delta case. Therefore, let me give you the definition in a general sense of what a continuous function is. So definition, f, which is a function from, let's say, x tau to y sigma. In other words, remember x tau is a topological space, y sigma is a topological space, where x is a set, tau is a topology, y is a set, and sigma is a topology. This function that maps one topological space to the other, in other words, this is the function from x to y as inputs and outputs go. X would be the inputs, y is the outputs. This function is continuous if for every single element of the target space topology, in other words, for every open set in sigma, the pre-image of that set is open in tau. So pre-images of open sets are open. And this is what it means to be continuous between topological spaces. Simply that pre-images of open sets are open. And we can see that pretty simply with this example here with f of x equals x squared. Okay. But let's take a look at an example of a more general or some fairly simple topological spaces. Let's say x is the following set. X is A, B, C, and D, and let's say the topology on that is going to consist of the empty set and X, and it's also going to be, let's say, the set containing AC. Okay, quickly verify that that's a topology. Remember, it contains empty set and X, and it's closed under arbitrary unions and finite intersections, and that does satisfy that. Let's say another set Y is given by, let's do 1, 2, and 3, and let's define a topology on that. Let's say we've got empty set, Y, and then let's say the set containing 1. Okay, so that's singleton. Again, that is going to be a topology. Now let's define a function from x to y. As follows. Let's say that f takes the point A to 1, f takes the point B to 2, f takes the point C to 1, and then let's say f takes the point D to 3. Okay? So my function, f takes the point A to 1, B to 2, C to 1, and D to 3. So A, B, C, D, again, this is my set X, and then my target space is the sets containing 1, 2, 3. Well, let's look at the pre-images of all the open sets, right? The pre-image of each open set must be open. Well, the pre-image of the empty set. Okay, Well, what elements map to the empty set? Well, there's no elements that map to the empty set, so that's empty. And this is open. Let's do the preimage of y. Preimage of y. In other words, remember the preimage of y is what maps to the set y. In other words, what maps to 1, 2, 3? Well, that would be all of x. And then, which of course is open. And then finally, what is the preimage of the singleton set? What are the elements of the domain space that map to the point 1 or to the value 1? Well, again, if I look up here at the function definition, what maps to the point 1? That'd be A and C. So the preimage of the singleton 1 would be the set consisting of A and C. And if I look at the topology on the domain space, notice that the set containing AC is an open set. Therefore, the preimage of every single open set, the preimage of everything in the target space topology is an element of the domain space topology. In other words, is open. Therefore, F is continuous. And again, thinking back to pre-calc or calc days, a sort of discrete function we would never really think of as continuous in a calculus sense, but in a much more abstract sense between topological space, this is actually a continuous function. Now, what I want to do is I want to sort of modify this example. Very similar type of a function, very similar sets and topologies, and do one more thing. Okay, so let me leave that up there for the moment, and let's say next example. Actually, I don't think that blue shows up as well. Let's try this pink right here. Okay. Let's say my set X consists of 1, 2, 3, and 4 again. Let's say the topology on that is going to be the empty set X, and then let's do AC, and then we'll do the singleton A. Okay, and then let's say the set Y consists of, again, 1, 2, and 3. And let's say sigma consists of empty set and Y, and then we'll do the set containing 1, and then I'll do the set containing 2. Oh, and then again, if it's a topological space, again, it also has to contain unions. So therefore, we also need to have 1, 2. Okay. So there is, and let's verify that that is a topology. Union 1, 2, intersection will contain the singletons. Yeah, that would contain unions and intersections. And then let's do the same function. So all I did is I modify the topology slightly, and let's see. Again, let's use the same function as the previous example. And let's take a look at the preimage of the open set 2. Okay, what maps to 2? Well, the only element within this domain that maps to the number 2 would be B. That means that the preimage of the singleton 2 would be the singleton B. But if I look up here at my domain space topology, the singleton B is not an element of that. Therefore, this function between these two topological spaces would be not continuous. Okay. So therefore, For continuity, we have really three different things that we have to take a look at. What is the function? What is the domain space topology? And what is the target space topology? Now, that's not something we ever had to consider in a calculus course, because without saying it in those courses, because it'd be beyond the scope of the material that you guys are discussing. But we always assume that the domain and the target space use the usual topology on the real line. Okay, we're not using any weird topologies there. But if I start modifying the topologies of the domain and the target space, we can either have, say, discrete functions that are continuous or discrete functions that are, as we expected, not continuous. Okay, thank you for watching, and please consider subscribing.